Unfortunately, this is not going to be a fun lecture. There's no creative visualizations that I know of. It is just math. One thing we will do is we will derive the full set of update equations for all the field components for full 3 dimensions and a PML at any axis. So it's a pretty general set of update equations that we will derive. And then from there, we will reduce it down to 2 dimensions or 1 dimension or whatever else we want to do for the rest of the semester. But you will have the full set of update equations for a fully 3-dimensional finite difference time domain. I felt that was the best use of time. So we will quickly review what we did last lecture. And then what we'll do is we'll pick up on Maxwell's equations in the frequency domain with the PML terms in there. The first task we need to do numerically is convert those equations to the time domain. Then we do our numerical approximations. We'll have some integrals that we need to approximate with summations. We have derivatives that we need to approximate with finite differences, and we have some other interpolations to do. From there, we will pick the field value at the future time step and solve for it and derive our update equations. And now you'll see, once we have the PMLs incorporated, that these update coefficients are very big and ugly. And it makes much more sense now of why we want to calculate those ahead of time. In fact, there's more math in calculating those than in updating the fields. And then the very last section, we will summarize all of the update equations. Essentially what we'll do is we'll step through and derive in detail one update equation, and the rest follow the exact same procedure, so we can just write them immediately. And so that'll be the end of this lecture. After this, we'll start talking about implementing these in 2 dimensions. So last time, we introduced the perfectly matched layer. And we said, unfortunately, in 2 dimensions, because the speed of the waves at the interface, because they're traveling at different angles, changes, we can't guarantee that the wave travels one grid cell in exactly 2 time steps. So we can't use this perfectly absorbing boundary condition that we use for our 1-dimensional code. We have to do something else. And that's the utility of the perfectly matched layer. So the concept of the PML is just building loss into the outer regions of our grid. But we do this in a way that also keeps the impedance matched. That way, building in loss does not also then introduce reflections. And it turned out we need anisotropic materials to do that. More specifically, uniaxially isotropic materials. And so we formulated that and how we could do it so that we zeroed out reflections for all frequencies, all polarizations, and all angles of incidence. And we collected this all into one big PML tensor, and we even formulated how we'll calculate our tensor components, the SX, SY, and SE, which are complex numbers. And what we'll see in this lecture is complex numbers lead to derivatives and integrals in our finite difference equations. We have the task of calculating these fictitious conductivity parameters. This is how we'll introduce the loss. And we have 2 of them to calculate. We calculate these over the entire grid. However, in the center, where we don't want PMLs, we just set these conductivity terms to 0, and then we taper them from 0 up to some large number as we move out. And this tapering is quite important. In principle, it's not needed. Numerically, it's very much needed, or we'll get reflections from those boundaries if we don't. And we ended the lecture with Maxwell's equations with our PML terms in there. And we even pulled out the S terms and put in the full expressions containing the fictitious conductivities. And this is where we ended it, and this is where we'll pick up today. The first step in deriving our update equations is to convert our frequency domain equations, which contain PML terms. We need to convert those to the time domain. So the first thing we will do is assume no loss. We've set our conductivity to 0. This is not the fictitious conductivity. Notice they're still here. That's our PML. It's just in this model, to be simple, we're ignoring the actual loss that we may want to incorporate with a device. It's not such a big deal if we want to keep that in. It's just a few extra algebra steps. But for simplicity and clarity here, we will ignore actual loss in a device. So these set of update equations won't incorporate loss due to a device, just from the PML. We have to manipulate our frequency domain equation so that it accommodates conversion to the time domain. And so to understand sort of the deeper principles here, we need to review some properties of Fourier transforms. So if we have an arbitrary time function, we would write its Fourier transform simply as a capital letter here and as a function of omega. So that's our notation. If we take our time function and multiply by a constant, that's really the same as the constant multiplied by the Fourier transform of the function. So we can just take this a to the outside, in other words. These last two are very important. If we take a time derivative of order a, so that could be a first or second order derivative, so a time derivative of this time function, and we're Fourier transforming that, it's just like we took the Fourier transform of the regular function and multiplied by j omega raised to the a power. So what we look for are terms being multiplied by j omega in the frequency domain equation, and that will become a derivative when we convert to the time domain. Likewise, if we see terms being divided by j omega, that really becomes an integration when we convert to the time domain. Or if we integrate this time function and Fourier transform the integral, we get the Fourier transform of the original function divided by j omega. So we keep these in mind so that we can rearrange our frequency domain equation that makes the conversion easier. So we'll grab our first equation. And so this was our first equation of the set of 9. And we'll notice 6 of them all look like this. So if we come up with our update equation from this, we can do the same exact procedure to all the other equations. So the first thing we'll do is we'll pull out this curl expression and just replace it with this CEX term. So we're writing it this way. The next thing we want to do is take this inverse term, this is Sx, the inverse of Sx, and we'll move it over to the right-hand side of the equation. So here it is. Then we multiply everything out, so we don't have anything in parentheses. And when we do that, we end up here. Notice we either have terms that don't have any j omegas with them, or we have terms being multiplied by j omegas or divided by j omegas. So either nothing, multiplied by j omega, or divided by j omega. That's important because the terms that are multiplied by j omega become time derivatives, and the ones being divided by j omega become time integrals. And the ones without any j omegas just essentially stay the same when we convert to the time domain. So getting to this last equation, it was important to understand those Fourier transform properties so we would know how to arrange it here. So here I'm color coding, and I'm going, I guess, in the order of the rainbow here. And term by term, we can write these in a time domain. So our first term, j omega hx, we're multiplying by j omega. That corresponds to a time derivative. So this term in the frequency domain becomes a derivative in the time domain. Over here, we're not multiplying or dividing by j omega, so it essentially looks the same in the time domain, that second term. Now the third term. Here, we are dividing by j omega. And so this whole term ends up inside an integral in the time domain. Fourth term, we're not multiplying or dividing by j omega, so it essentially does not change for the time domain other than our omega becomes a t. Then our very last term, we're dividing by j omega, so this whole expression becomes integrated over time. So we went term by term using the properties of Fourier transforms and converted each one over to the time domain. So here's a summary of what we did. Term by term, we went from our frequency domain equation with our PML parameters to a time domain equation with PML parameters. And notice we have integrals inside of these. So while our finite difference time domain is running, we'll have to be calculating these integrals. So things slow down a little bit. If we had done this to all of our equations, that same procedure, all 6 or all 9 of our frequency domain equations, this is where we'd end up. No reason to repeat that because the first 6 look exactly the same as deriving the time domain equation of the first. So this very top equation is the one that we derived step by step, and the rest just fall out of that. And of course, these are effortless to convert from frequency to time domain. So we have our time domain equations. Our next step is to approximate these numerically. Our integrals become summations, our derivatives become finite differences. So here's a repeat of our first equation in the time domain, and here's the 5 different terms that it contains. We will handle each one separately. The first term, we've already done this. This is the time derivative of the H field. We'll define the magnetic fields to exist at the half time steps. So this finite difference actually, when we do this, exists at the integer time steps, which is compatible with the electric field quantities. So term 1 we've already done. That's an easy one. Term 2, we have a bunch of constants here. They don't change. And then we have an H field. But the H field is designed in our finite difference scheme to exist at the half time steps. Well, here we need one that exists at an integer time step. So how do we do that? We interpolate. We average the H field at the future time step with the H field at the previous time step. And so if we average that, we are interpolating the H field to exist at time t instead of t plus delta t over 2 or t minus delta t over 2. So not too tricky. This is the difficult term, the third term. So we start with this integral, and first thing I like to do when I'm presented with a difficult integral is I figure out what are constants and I bring them to the outside of the integral. So these are constants. They don't change as a function of time, at least not how we're formulating it. So we're just left with really integrating the magnetic field. Well, let's just make a guess. Let's just replace this integral with a summation. Now the H field exists at half time steps. So we have to integrate from delta t over 2 all the way up to a t plus delta t over 2. But our integral only went up to time t. We've integrated too far. We've integrated a half time step too far. We could have chosen to go up to t minus delta t over 2, but we'd have a similar problem. We would have been missing. We wouldn't have integrated far enough. We would have been missing half of a time step. So something needs correcting here because we have to integrate up to t, not t plus delta t over 2 or t minus delta t over 2. Somehow we have to integrate up only to time t. So this top equation is where we were on the previous slide. And this summation is incorrect, remember, because we've integrated too far. So what we can do is we can take this term and pull the last term out, and we only sum up to t minus delta t over 2. But this term we pull out, we only want to integrate over half of a time step. And so now we've fixed it. We've only integrated up to time t instead of t plus delta t over 2. But we still have a problem. We have an H field here that exists at t plus delta t over 2. We need this to exist at time t. Well, like we did previously, we'll just average. So we will average the H field at the future time step with the H field at a previous time step. So we're just averaging. And we still have this delta t over 2 because we only want to integrate over that final half time step. So we did it. Another thing we want to notice, looking at this summation, we are summing up to t minus delta t over 2. Eventually, we're going to be updating our H field to calculate what it is at t plus delta t over 2. That implies that we need to update this summation before we update the H field. And another thing we did on this step is there was a delta t over 2 and a delta t. We pulled that constant to the outside. And this also gave us a hint in the order that we have to do things. Term 4. This is an easy one. This is just the curl operation. So nothing has changed here from previous lectures. The last term is similar to term 3. We have an integral here. The fortunate news here is that we're integrating a term that exists at integer time steps, so that will be possible to integrate up to time t exactly without doing anything tricky like we did for term 3. So we pull our constants to the outside of the integral, and we're just left with integrating the curl term, which we can approximate with a summation. No problems here. We sum up the time t, and there's really no issues. So the last thing we'll do is we'll pull delta t out, so we're really just summing the curl terms without the delta t. We can do that at the end. But if we look at this, that also implies we are summing up the time t, not t plus delta t over 2. So again, that implies we will update this summation before we update the E field. So what the heck happened here? We started with this big ugly time domain equation, and we derived an even bigger and uglier numerical approximation of that using summations and finite differences. Now if we did that same procedure with all of our time domain equations, this is where we would end up. And no reason to repeat that. It's exactly the same math. In fact, if you're sharp enough, you can write the other equations just by inspection, just substitution of variables, because the initial equations look the same, so the final equations look the same. And the last thing we're going to do here is derive the update equations from our numerical approximations. Again, we'll proceed with that first equation. This is where we ended up with going from our time domain equation to approximating everything numerically. Our derivatives became finite differences, our integrations became summations. And our object now to derive the update equation is to solve for the h field at the future time value. Well, that occurs 3 different places. So clearly we have some algebra to do. We'll multiply everything out, collect the terms, keep that h field on the left, move everything else to the right, etc. So first thing, expand the equation. So this top equation was our starting point. After we multiply everything out, we end up here. Then we collect all the terms. So our h fields only occur one time. So here's where we were on the previous slide. After we collect all the common terms, this is where we are. And notice I'm keeping this h field at the future time step highlighted in red so we can track it. And now we need to solve for it. And when we do that, here's where we end up. This is our update equation. Look at our update coefficients. Look how big and ugly those are. But these are all constants. They don't change over the course of the simulation, and it makes a lot of sense to calculate these ahead of time. But the anatomy is still the same. We have h field at the future time step equals the h field at the previous time step plus a lot of correction terms or update terms. So, but we have much bigger and uglier update coefficients that we calculate ahead of time. So let's write this in a slightly different form. So the equation on the previous slide is written at the bottom. The difference is these big ugly expressions I'm calling update coefficients. And these will also be on arrays the same size as how we're storing the fields. So the first thing we'll do before even the main finite difference time domain loop is calculate these update coefficients. And these are arrays across the entire grid. Then as the thing is running, immediately before we update the h fields, we'll update our integration term where we're integrating the curl. We'll update our integration term where we're integrating the magnetic field. And we'll also calculate the curl. And once we have these and our update coefficients that we calculated ahead of time, then we can implement our update equation. So that's the final form. But the equation on the bottom really is the same one as on the previous slide. So that's it. That's the whole derivation of the update equation. These are a lot bigger and a lot uglier, and the reason being because of the PML. That's really what gummed up the works here. We can do a test to see if these are correct. If we pass the test, it doesn't mean absolutely they're correct, but if it didn't pass the test, it would certainly mean that they're wrong. So what we can do is turn off the PML and see if our update equation reduces down to something that looks familiar that we've gotten previously. Well, if we turn off the PML, those fictitious conductivity terms all go to 0. And when that happens, our update coefficients reduce to this. Notice these last two update coefficients are the one multiplying our integrations. So our integrations are no longer there, which makes sense because they weren't there before we introduced the PML. The update coefficient multiplying the previous H field, so here's the previous H field, goes to 1, so there is nothing here. And we end up with the update coefficient that looks familiar from previous work. And so here's our reduced update equation. Then if we reduce this to 2 dimensions, our z derivative goes to 0. It goes down to this, and this is exactly what we saw in lecture 11. So this does not mean we are correct. It's a good indication of it, but if we didn't pass this test, we would definitely have something wrong. So in this last section, there's really nothing to discuss. It's just a summary of the update equations for all 9 of our equations. This is the first one, the final form of the update equation for h of x. This is the one that we derived in detail. And we write all the other ones really following the exact same procedure. So we have an update equation for hy here. Another update equation for hz. Then similarly, we have update equations for dx, dy, and dz. Now in one slide we can write update equations for the E field from the D. This is just a constitutive relation, so this is pretty much easy and effortless. So what I've left you with here are the update equations for a full 3-dimensional finite difference time domain for PMLs at all boundaries. So it's really sort of the most complicated case, and from those equations, we can reduce down to whatever we want to do. We can reduce down to 2 dimensions, 1 dimensions, turn off the PML, turn it on, do whatever. So you're left with a really generic set of update equations. And so that's it for this lecture.